Welcome to the day one panel discussion of the SNIA PM+CS Summit. We have some great speakers for you that have presented already. If you haven't had a chance to review their talks, maybe this will give you a flavor of what they were talking about. And if you are looking forward to more on this topic, ask your questions in the Slack channel, and we'll try and get you answers real time while this video is airing. Who do we have here today? Well, we have several people. Not all of our speakers were able to make it from our main stage, but Jim Handy is here. He's going to be talking about the memory wall. Stephen Bates is representing Nvme and what's going on for computational storage. We also have both JK from VMware and Michael Messner from who's going to be talking about, from Intel, talking about computational storage in the virtualized environment. Chris Peterson, a frequent presenter, is talking about AI memory at Meta. And then finally, we also have Andy Rudolph, who's going to be giving us that update about persistent memory today. I'm Dave Eggleston. I'm an independent consultant, really looking forward to this panel. Let's go ahead and get started. And one of the key questions or key points that was made during the talk by Jim Handy and Tom Coughlin was, what are we trying to solve? They talked about it being a memory wall, and we want to be able to break through that memory wall. Jim, you talked about the big problem we're trying to solve is inefficient data movement, and that's caused by the network. Why don't you tell us a little bit more about that?
Yeah, it's not just the network, Dave, but it's also the memory interface and the interface to solid state drives, hard disk drives, is that these communications channels are a whole lot slower than what's on either end of it. You've got fast flash going through a slower channel into an extremely fast processor, or in the case of memory, you've got DRAM trying to talk through that. But it's something that we've seen for years with network storage, is that you've got, you know, a milliseconds delay of getting the data across there. And so you're motivated not to do that very often.
But why not fix the network, Jim? I mean, you know, if the network is the problem, why not just fix the network? Then our problem's solved. We don't have to worry about it.
Easier said than done, though. This is
what's
one of
the
those
barrier?
Things. Yeah. Well, the barrier is mostly just physics. You know, it gets down in the case of memory to how fast can you move electrons up and down a wire that's got characteristics, capacitance and resistance, that slow it down an awful lot. In the network, it's more related to noise issues and, you know, how fast can you switch signals up and down before there starts to be enormous crosstalk. So, you know, anytime that you can get past doing that, then you don't have to solve the network problems. And that's something that can be done architecturally, whereas the network problems, I've heard people say that only God can solve those.
And so let's jump quickly to Stephen Bates. From Nvme's perspective, you know, Nvme has been working on this for quite a while. How are we getting this addressed in terms of this inefficient data movement? How is Nvme tackling this problem?
Thanks, Dave. So Nvme has been incredibly successful as a storage protocol. I don't think anyone will doubt that. And you know, the continued rise of Nvme as a storage platform, the amount of data that we're now storing on Nvme just makes it a very ubiquitous and successful protocol. But because now we're storing so much data on devices and media that's behind an Nvme interface, back to you know, what Jim was saying, moving compute to the same area as that Nvme topology, it starts to make a lot more sense. You know, imagine if you're storing petabytes or even exabytes of data, and you want to ask questions of that data, because the reality is storing data isn't particularly interesting. Gathering meaningful inferences from that data is incredibly important. So how do we get answers from our data? Well, either we pull all that data off those Nvme devices to central processors and run our data analytics there, or we push the analytic questions down to the storage layer. And so there's many companies that have started looking at this, including companies as large as Amazon Web Services. And they've come to Nvme asking, can we develop a standard around this? Can we take these ideas of pushing compute to the storage layer and create a vendor agnostic open standard. And that's really what Nvme is chartered with doing. And that's what the task group that myself and Kim Malone and Bill Martin from Samsung are working on.
Got it. We'll come back. Yeah, we'll come back later and ask some questions about that task group. And particularly, I think you had quite a bit with you and Kim talking about your Nvme namespace, but also having this new computational namespace that's going to be a key part of how you standardize that going forward. But let's jump over to Michael and have you build on that as well. You talked about in Intel, you've built up this computational storage research platform, and you shared some of the information about that. How do you see Intel driving that space forward in computational storage? And again, kind of the same point. How does computational storage address this inefficient data movement that Jim talked about?
Yeah, well, as you can imagine, Intel is really interested in anything that requires compute silicon, right? And as Stephen was saying, the challenge is keeping the silicon fed with data. Right, so one option, make I/O faster, make the network faster, make PCIe faster, the CPU memory complex. And people have been doing that and they'll continue to do it, but it's much easier at this point to just move compute down to storage, right? So what can Intel do to drive that? Well, we're already involved in the standards organization, and Stephen's working with Kim Malone on that. But there's a big missing component. So if you look at the lowest level at NVMe, that's the wire protocol. But what happens in system software? What happens on both ends? And what we're seeing in the industry, basically industry-wide, is there's a lot left to the imagination as to how computational storage is really going to be realized from an end-to-end perspective. And so I work in Intel Labs, and we see a research opportunity there. So starting with applications and looking top-down, what is it that they need to offload? How does this influence or impact the standard once that takes form? And then what are the silicon opportunities on the back end? So we've basically built out a multi-year research program just to answer these fundamental questions. And the goal ultimately is to feed our results into the standards organization to make sure that this doesn't turn into a niche solution. Because I think that's what most folks are worried about. Computational storage goes back to the 60s with database machines, but it just never really took hold. But I'm thinking this is the decade for computational storage because the problems are real, and we've got Intel support.
And I think we'll come back and talk, because I think both for persistent memory as well for computational storage, having that software layer is really, really important to enable it. So I know certainly Andy Rudolph's going to talk about that, and we'll discuss that a little bit further. But let's bring in Yang Qi from Samsung. Yang has also posited that there's a really important element for computational storage in reducing power. And Yang, please fill us in about that. You had some compelling data talking about how that can be reduced and why we need to reduce that for our data centers.
Yeah, so I started the computational storage research 10 years ago. And at the time, the main benefit of the computational storage is to reduce power and also can improve performance. But most people talk about the performance, but actually what is the overall benefit from rack scale architecture and the energy consumption from the system to do the same computation. So the study we did is if you build a rack system based on x86 and compare that to the computational storage, which is based on ARM processor and high performance memory technology, then what is the potential benefit you can get out of it, and what kind of application can be run on that kind of device. That was what we did, and based on the study, computational storage, due to the power limit, we may not able to run very compute intensive applications. Instead of doing that, if you're focusing on the more or less IO intensive application, what I mean by IO intensive application in terms of arithmetic intensity, which is commonly used in the machine learning domain. If arithmetic intensity is not that high, around less than 100, the sweet spot looks like around 10. If you run that kind of application, then the computational storage can actually handle that kind of workload very efficiently with very low power. So if we sum up all the power requirement within a rack, the standard rack, then the using x86 is consume more power, more than 40%. compared to the computational storage. So this is actually very important. Now, many people talk about the carbon neutrality, and it has become real. And I actually read one article yesterday. We have only 1.3 or 31 degrees Celsius left to meet
Yeah,
the
so
1.5.
we're definitely getting close to some limits. I did have a quick question for you. You're using an FPGA. FPGAs are known for consuming a lot of power. Is there a path here towards an ASIC, or does the FPGA give you that flexibility that your customers need to try out different solutions with computational storage?
So FPGA is more like a stepping stone. I don't think FPGA is going to be the ultimate solution because, as I mentioned, computational storage basically playing the game of performance per watt. Whether FPGA is going to provide a better option for that, I don't think so. So eventually, FPGA going to be replaced by the ASIC-based solution at the end. But right now, we have lack of application and the flexibility of the platform in terms of performance and the programmability. We have sort of the kind of the middle age right now. So because of that, we adopted FPGA to broaden the market and the application. But ultimately, I think we need to go to the ASIC-based one.
Got it. Okay, let's continue. One more question on the computational storage. Back to JK. JK, in your presentation with Michael, you talked about the need to virtualize the computational storage from where the processing elements are. What's the advantages to that? Why do virtualization at all? Don't you lose some performance in doing that?
Not really. In reality, in data center, the most of workload run as a VM or container instances. So if we want to take advantage of the computational storage devices, we need some way to access the computational storages through the VM instead of bare metal hardware. So what is getting interesting for us recently, the Nvme standard committee or SNIA computational storage task group working on the Nvme spec to add the computational storage command set, which can be emulated by software or SmartNIC. In that cases, our virtual machine and container easily can access or share those devices more effectively. Then eventually we can integrate the application and storage node more friendly to virtualization. And as you asked whether we lose some efficiency or not, we are actually getting more efficient by sharing the same expensive physical hardware with the multiple instance of the VM and container workload, because not always we are using that expensive resource all the way, right? So having the virtualization support will be critical for the success of this computational storage devices. That's what we believe. The VMware has a long history of having the storage offload, vSphere API array integration, actually offload the data move and then data zero kind of operation in the SCSI world. So we get a big advantage of the moving such operation near disk array. In the same way, what we believe this computational storage device advantage, what people show can be mostly maximized with the virtualization support.
Got it. Okay. Yeah, that makes a lot of sense. I think also Michael made the same point that the sharing of resources is something we have to consider. And sometimes we don't think about how widely shared some of these resources can be. Now let's shift gears. Let's talk about persistent memory. We've kind of done a speed round on computational storage. So I want to go to Andy Rudolph first. And Andy, you said one of the big learnings from the Optane product experience at Intel was how powerful the pull is for memory tiering. Why is that? A couple questions for you there. Why, first of all, why was that a surprise to you folks at Intel, and how do you see that playing out as things go forward in the future?
Yeah, that's a good question. You know, from the beginning, the Intel product supported both a volatile use case and a persistent use case. And we saw the persistent use case as requiring quite a bit of ecosystem development, learning how to program with this new kind of persistent programming model, learning how to really leverage it. The upside is also pretty huge. And so, you know, I spent most of the years leading up to the release giving talks about, you know, persistent memory programming and how cool that's going to be that you can use the persistence. And of course, I still believe all that, and we've a lot of use cases that are doing that. But the volatile use case basically doesn't require any changes to your program. In fact, even the OS itself can run without changes. And so when faced with, you know, building a system and looking at the cost that you're paying for DRAM and looking at ways to reduce that, volatile use case sort of pops up as a very quick and easy way to get some relief on the system cost. And so, you know, we always knew that would be one of the options. But the reason I say I'm surprised by it is that it has grown way faster than I expected it to grow, because I was pushing people so hard on the persistent side, and I still am. So, you know, I think both of those will continue to grow. One more thing about memory tiering in general, you know, it's kind of worth just sort of looking at the history. If you've been around a long time, you might remember when there were operating systems that just did swapping, right? And that is really a type of memory tiering, right? It's moving things from a slow medium to a fast medium. And then, you know, swapping begat paging, and everybody thought, oh, this is wonderful. Now we can run, you know, way more jobs than we have memory for. And then pretty soon the need for performance caused people to get bigger and bigger memory. And now paging is suddenly bad. And it's horrible. Oh my God, you're paging, you're broken, you know. And I'm here to say it's back, right? And it's not paging that's back, but it's memory tiering that's back. Because we're going to see these different hierarchies of different types of memory, not just persistent memory, but all kinds of different memory, and with different latencies, because of, say, you have some memory that's attached to a DDR slot versus some memory that's attached through several switches on CXL.
And that's
So,
definitely one of the complications that even some of our speakers tomorrow are going to be talking about, both the memverge solution, some of the work in SDXI that's going on memory data movement, kind of gets at this issue of how do we handle this kind of environment. And I do want to come back around a bit later, Andy, and ask about your 2x2 matrix there. You know, marketing says everything can be solved and summed up in a 2x2, and you've done that neatly in your presentation. So thank you very much for that. But let's bring in Chris Peterson. Chris, you talked a lot about AI, what the driving needs are for AI, how you consume memory, and you made a case for, in the memory pyramid, having this tier that's a little bit below DRAM, that you can tolerate a little bit longer latency. Why don't you talk first, though, about what from AI is driving those requirements? You zoomed in specifically on the DLRM requirements, and give us a little more color on that, as you're certainly a system guy getting into that data.
Sure. So I forget who mentioned this earlier, but it's great to store that data, but actually analyzing it and doing something useful with it is really the goal, right? And a lot of AI is doing that, right? What these AI models essentially do, in particular, the recommendation models that I'm talking about, are basically taking all of those inputs, all of that data, and trying to make a suggestion for something, right? They're trying to perhaps branch predict a search selection, or give you a suggestion on what videos might be interesting to you, right? And the only way all of that works is if you have a lot of data near those AI models. And what we've found is that those models are growing at effectively an exponential rate, right? So the size of these things, to be able to make accurate and reasonable predictions, it needs a lot of data to process. And the challenge that we're seeing is that the underlying memory hierarchy that we've been working with for many years now is just running into a lot of truly physical challenges, right? We're having a hard time scaling DRAM cell technology, for example, and it makes sense, right? The traditional scaling approaches that we've used, so going even beyond DRAM die density scaling, things like adding memory channels, stacking DRAM components and so forth, are also starting to run out of gas. So we're kind of getting into this like perfect storm of trying to scale memory capacity. And I think what we're observing is that we need a different vector to be able to scale.
And I think Cholmin Park, who unfortunately was not able to join us today, was talking about how CXL for memory does solve some of these problems. And I know certainly at Meta, you've looked into that. Maybe give us a little more idea about why is it that CXL is so attractive in solving some of these AI problems?
Yeah, absolutely. So I think one of the big pieces here, and it's something that Andy was just alluding to, right? I don't think we talk enough about the importance of transparency to software. I think we talk a lot about, hey, I can optimize software for this new hardware technology or this new architecture and so forth. And you're right, we can and do that in many cases, but the reality is we cannot do that everywhere. Even at our scale, right? We have thousands of applications. We can't optimize all of them. And so one of the beautiful things about CXL is that we can truly treat it and map it as system memory, right? So it, in many ways, it is transparent to the applications themselves.
So you're saying that is bringing something new to your system then, in having this capability rather than more the, let's call it the direct in the box connection to DDR. You've got some more ability to abstract, you've got some more ability to share that you didn't have before. Why is that particularly helpful for AI at Meta?
Well, I think it's particularly helpful because one of the challenges that we run into is if we cannot put these AI workloads on a single machine, really the traditional solution to that is you scale out, right? So you end up having to split these workloads across multiple machines, and you get these weird end scaling effects. And it kind of actually gets to Jim's point about the network becoming the bottleneck at that point, right? Now you have to deal with all of these machines who are processing essentially the same queries, and then you have to aggregate them somewhere, right? All of that takes time. It adds a lot of energy in terms of power, and it adds a lot of operational complexity as well, right? So anytime we can simplify and keep things on one machine, and that's really what like expanding capacity on one machine can help us do.
So let's get this theme of memory going. Back to you, Jim. One of the things that you talked about with Tom is this new old idea of process in memory or process near memory. What's going on in that space? And does that kind of solve our problem here of inefficient data movement? Why wasn't process in memory adopted in the past? Why are we seeing it pop up again as a research topic?
It's always been a popular topic for people to talk about because there is logic inside of a memory chip, and it's the chip's process has been optimized for making bits, and so it's never really very good logic. It's never very fast, but you've got these phenomenally wide data buses all over the place inside the memory chip, and so if you can run that slow logic on very, very wide data channels, that offers you a speed advantage. But also, if you don't have to move the data out of the chip and then back in again, then that gives you a great savings both in power and in the speed, and also in the amount of the processor's time that must be used for that kind of a thing.
I see.
Yeah, but the reason you asked why it wasn't already popular, and the reason why is because the way memories work is you have to make tens of millions or more of these chips in order to break even. And until somebody can prove that there's a market for compute and memory chips at that kind of volume, then they'll always end up being a lot more expensive than a standard memory chip. They also require special software support.
Yeah, so that's truly the process in memory. I've seen some interesting work on the process near memory, which kind of gets back towards kind of what I've seen from Ididicom on computational storage. So Stephen, if seeing as how you're using a lot of local memory inside your NVMe CS architecture, doesn't process in memory eliminate the need for computational storage? We can do it in memory. Why do we need computational storage? Give me a case for computational storage versus PIM.
I think it goes back to what Chris was alluding to. Memory is always going to be less dense and more expensive than capacity storage like NAND. So the problem that you have, and also goes to Jim's point, is as soon as you try to do something that affects a huge commodity market like DRAM or NAND, customers aren't going to take it because it's a little bit more expensive than just getting it without the compute. So I think we need to do computation near data, and whether that data is memory-centric data or more block or page-centric data, I think depends on the application. Okay. And so I think we need both. Right?
So the concept overall has a lot of merit, like you're saying, compute near the data, whether we're doing an IO access or we're doing a load and store access. Well, that doesn't really. Could you see? This is my question. Could you see a layered solution?
Totally. And in fact, the industry, myself and others, we're having more and more conversations around the fact that in the next few years we are going to see data center servers that I guarantee will have both CXL and NVMe in them. And we're having discussions around what does that mean? How are people going to deploy these two different protocols? And these two protocols are moving closer to each other. NVMe is adopting memory-centric namespaces for things like persistent and non-persistent memory, which sits in computational storage. And CXL is adopting things like accelerator interfaces through CXL.io. So, can I envision a world where CXL and NVMe coexist? For sure, that's going to happen. Now, exactly what those coexistence models look like, I think that's a really interesting area.
Yeah, and I guess that's part of my question. Could you see inside a computational storage device, you could see it actually also taking advantage of process in memory or process near memory? That's also okay. Interesting.
Yeah. And also tiering, right? So putting NVMe devices behind CXL for tiering of memory and essentially paging in the background. Back to what Andy said. These are all things that I think we'll be able to do. Now, whether the market adopts them or not, I think is going to depend on the nuances that some of us are working on. It's a fascinating area.
We'll come back to that in a minute and talk about the software, because I think that's an incredible, many of you have talked about the software being an essential element to enable adoption and making that as transparent as possible. But while I'm still talking to Stephen here, let's talk about this new idea, or at least to me, new idea of computational namespace. We have the NVMe namespace, but now you've got this, you had a nice chart which showed NVMe namespace, local memory, and then computational namespace. How does that solve this core problem of inefficient data movement? How does that help you by having this separate namespace, computational namespace?
Yeah, so NVMe has always used this architectural concept of a namespace. This is an entity that sits behind an NVMe controller or more than one controller if you have multi-controller environments, and it allows us to treat that as essentially a destination for NVMe commands. Now, as you alluded to earlier, NVMe command sets, there are more than one. Like originally there was just one that was for NAND in an LBA type shape. Now we have a key value command set. And what we're working on in 4091 within NVMe is a computational command set. Now the advantage of doing this using compute namespaces is it solves a lot of problems around multi-controller environments. It's a concept that's already well understood. And back to one of the earlier comments, it helps a lot with virtualization, because namespaces are something that we already use in virtualized environments. You can take the capacity of an NVMe device, carve it up into multiple namespaces, and hand those into VMs that are running in a untrusted multi-tenant environment. So it's a really nice concept for treating these computational elements and sharing the compute resources across multiple VMs.
Interesting. Okay, so let's jump back to Andy Rudolph and let's kind of now turn the crank and talk about software. I alluded to Andy in his talk at a beautiful 2x2, talked about persistent memory, volatile memory, and then transparent and then non-transparent to the end application. Andy, talk about that, especially that transparency vector. What are you getting at there, and why is it important to make things transparent to the host application?
Yeah, I mean, of course, there's the obvious point. If you have thousands of applications out there and you want a technology to be used by them, you don't want to wait for thousands of those applications to get modified and retested and redeployed. But the thing about transparency that I think isn't very well understood by a lot of people is that it's a matter of perspective. If I make a version of Cassandra that knows intimate details about persistent memory and leverages it, the applications that use the Cassandra API are still unmodified. So is that a transparent use case or not? Well, in most of us would say that's not transparent because a user space of code had to change. But of course, the thousands or many thousands of applications that use the Cassandra API don't have to change. So I would claim that that's transparent above a certain level. And so that's really the way to look at it is, my matrix is an easy thing for people to understand, the 4 quadrants. In a lot of ways, it's too simplified. It's not really, are you transparent or not? It's at what level is it transparent?
I
things
see. So
above that level.
It's kind of gradiated. There's a
Kind of,
grayness to it. It's not a black and white marketing 2x2. It's not that simple.
And the kernel tends to be, like one of the most popular levels where you add the knowledge, you add, things where the kernel understands that there's different types of memory and so on. And then everything running in user space doesn't need modification. But I just wanted to point out that sometimes that layer of transparency is pushed up a little bit. So you have some middleware or some libraries that know about the new hardware features of that. Maybe the applications don't. And so even the stuff that Stephen was talking about, the computational storage, you could imagine somebody using a library and being completely unaware that they're actually leveraging computational storage because the library was modified, but the app was not. So pretty much, for all of the technologies that we're all going around talking about, you have to look at the software experience that the developers are going to face.
And with again, memory tiering, and doesn't that make it even more complicated? Because now we were dealing with just a bank of or a certain pool of DDR. Now we've got memory spread across various places, and it seems that to get the proper adoption, those things are going to be in place. One of the speakers, Cholman Park today was talking about this SMDK. That's an open source software that I believe is authored by Samsung, not completely clear to me, but that they're offering for the heterogeneous compute. So it seems like that's going to be an important element, but there seem to be a number of these elements going on. There's also the VMware, the Capitola that's going on for enabling that. So it seems that to get people to use PM+CS software and making it as easy to adopt as possible is a key element. How much of that has been an issue to overcome on Optane adoption?
I mean, we got a very early start on it. Many of my workers here were involved with the Nvme programming work that we did, and that was years before it shipped. So that helped a lot. But of course, I like to say for an enterprise level application, if you even change a comment, you have to retest the entire application and get everybody to redeploy it, right? It's not an easy thing. So I think we overcame the technical challenges of the software programming faster than we overcame the barriers to adoption, because I think it takes a long time to adopt changes like that.
Got it. So let's jump to Michael. Let's talk about this as well. For computational storage, what is the role of software in enabling the adoption, and for what applications do you really see computational storage getting that mainstream adoption?
Yeah, so I think software is the make or break technology for computational storage. Let's say that the Nvme standard, it was done today, right? Without the appropriate system software support, we basically have to rely on application developers to program at the lowest levels, and a number of optimizations will go missed, and some folks will just give up and say, that's not my job. So I think we need software libraries, we need kernel support to make sure that when you see a computational storage device, it doesn't look foreign. If you wanted to offload, for example, a simple search operation, right? Something that works a lot like grep. but maybe you point grep to an NVMe device. That's the kind of simplicity that we're looking at. Or maybe you go a little bit further up in the stack and you look at someone mentioned Cassandra. Well, there's Cassandra, there's HDFS, there's MinIO. There are a number of big, object storage stacks that could benefit from computational storage by themselves, right? And so giving them an API that they could understand, like Andy was referring to program computational storage is key. And then eventually open up that API to the developers, the actual folks actually using that. Let's say that you wanted to do a filter operation before going into a deep learning pipeline. Maybe you wanted to crop an image. Maybe you wanted to filter out some unnecessary data. Having an interface that would let you to do that leverages the existing models that these folks use today without having to adopt a completely new programming model, we think that is key, right? So one of the things that we're looking at Intel is to see how can we modify some of the middleware to start with, to make sure that we get computational storage, give it a foothold with big system software. So again, HDFS, MinIO, Cassandra, some of the big stacks. Once that's there and we can prove out that not moving data around unnecessarily has a system-wide benefit, then we open up the interface a little bit more and let those filtering operations, for example, be exposed to the end users, right?
And I can imagine that JK representing VMware here. VMware has a really central role in this. Maybe JK, talk a little bit more about what your company is doing to enable computational storage and the memory tiering that we alluded to earlier, and how does that fit in with some of the work that you've been doing?
Yeah, as you mentioned, we have a project have been the tiered memory support, which is a project Capitola, and then we also have a project called Project Moderator, which actually is the SmartNIC project, and then we moving the storage and networking and management component to SmartNIC as the same as AWS Nitro. But we are actually going further. We are not just simply the virtualized device as a software, we also emulate as a hardware, which actually give us much broader adoption of the workload as the bare metal. And
for persistent memory and computational storage, are there certain hooks that are missing that you need to get better visibility of the hardware? Is there something that you would ask the community to provide that you don't have today?
Yeah, so another thing we are observing as a design pattern for cloud application, they are actually prepared to have the larger scale, right? And then the way of doing it, they are disaggregate the software logic, application logic. For example, the AWS Aurora, they are disaggregate their database engine from the database upper part and lower part, and then they are moving the lower storage engine part to storage node. And then those nodes actually running as a separate instances to scale. So a lot of the cloud native application run that way. VMware try to support such cloud native application with the Tanzu and Kubernetes services. And then when we come to the this type of new application and then new hardware like the persistent memory and computational storage devices to combine and SmartNIC, and then how we actually provide the composable component as a system software people to build such distributed software, right? So the way we are offering the such capability, we still stick with the virtualized a lot of component like the storage devices and the network devices, and then even the persistent memory. We have a lot of virtualized component. So in that way, people compose those components more flexibly, and then they can build such disaggregated application more easily. So this is what I show with the Intel and the MinIO example cases. We disaggregate the application AI ML, and then MinIO also disaggregate the sum of portion as a upper layer, and then down the storage specific layer, they just try to use the CSD initiator and target, and then they can separate. And then they are also run as a VM with the virtualization support, and then they can fully utilize underlying the computational storage device offload functionality. So that is very good example we try to show. In the end, in the future, this distributed and then much more scalable the cloud native application cases, such the hypervisor virtualization support with the certain architecture will really help.
Okay, let's bring in Yang too. Yang, what challenges have you had in getting the software in place for computational storage to be adopted by the end customers, the system builders?
Yeah, so the one of challenge is we already talk about the programmability, but the Nvme standard body introduced TP4091 and the SNIA introduced the API. But what I see from the end customer perspective, those are handling more like a control part, not the programming itself. And the common request from the customer is, I want to my C code into device seamlessly. So that is actually common request from the customer. And then they will think about the performance after that. So whether the current ecosystem is mature enough to accommodate that kind of request, we are far behind. So people talk about the framework level, the programmability or the user-friendly access. There are multiple layers, but some customer may consume a different layer, but eventually end customer want to just the surgery their application, just put it into the computational storage. There's a big gap because as I mentioned, the Nvme standard and the TP4 and the SNIA API is more like control API, not like programming API like a CUDA, or even if you are using the one API from Intel, they are actually layer, actually abstract the hardware, and the user can actually consume the hardware abstraction and map their application to the hardware abstraction. CUDA has it, AMD, Broadcom has it, and one API leverager has it. So usually the most accelerator have their abstraction layer, hardware abstraction layer, and build software on top of that, and the user have a clear idea how to use it. But right now the computational storage is not mature enough to provide that kind of abstraction yet.
Okay, and thank you for filling us in. Now we're going to go to a real quick speed round on one question. And I'm going to start with Chris Peterson. Chris, what is the role of persistence going forward? CXL DRAM, we said, is going to be a thing. What's the role for persistence?
So I do believe that there are some targeted use case for persistence. It's not a big focus area for us. Certain areas that might be interesting are things like write buffers or write caches. Could be very interesting. But in general, for us, we primarily view it as a main memory extension, right? So another tier of main memory. And at least in the near term, we believe that to be the most interesting of use cases.
Jim Handy, what's the role of persistence?
It's interesting. It doesn't find its way into the world that all of us play in so much as it does in little things like fitness monitors, where, and who knows, heart pacemakers, where the whole device has to be shut down as often as possible to save battery power. But if you look way off into the far future, and in our report we look at to 2032, we look at how chips are going to be designed in those days, and certain technologies are not going to be able to be made anymore. In particular, NOR flash and SRAM are very unappealing. And so persistent memory is going to find its way inside of microprocessors and ASICs and other chips like that. And when it does, then people will find a way to take advantage of it.
Do you see that as being integrated as embedded memory, or do you see that as like UCIe, where it's chiplets which are fitting together?
It's hard to tell. The chiplet approach is really good because it allows different chips to be made using different processes. But we're way early in the life of UCIe, so where that's about to go is unclear.
Just kicking off, yeah. And Cholman Park did a very intro to UCIe as well. I think when he showed handheld to server, I was a little surprised by the handheld part. But Stephen Bates, you've got an opinion about everything. What is the role of persistence?
Well, I mean, I think to Chris's point, a lot of people are going to use persistent memory in volatile mode. I think AI, as Chris pointed out, just leads to the requirements to have massive memory footprints in single servers or in small numbers of servers. And so it has a role to play there. Obviously, Nvme has been hugely successful with regards to persistence. It's not byte addressable. It's not persistent memory.
Yeah, and I think we can all agree that in storage, persistence is absolutely necessary. We definitely get that. But in memory, is it really necessary?
And I think what's very interesting, UCIe, the comments on UCIe, are we going to see programming interfaces over UCIe? Do we need an Nvme transport over UCIe? I think these things are very interesting. And as we move to more memory-centric namespaces in Nvme, can we leverage that, or should it be CXL? So again, it's a very exciting time. I think Jim's points are really well made. Like, can we use persistence to drop power when we're not actually needing that data for that particular period of time, which could become a very small period of time, right? If it's an on-chip or in-package, not persistent memory technology.
Andy Rudolph, you got to bring us home here. What's the role of persistence? I remember Andy Rudolph, give me DRAM with a car battery. I don't care. Whatever it looks like, I'll take it. Andy, what's the role of persistence?
I'll concentrate on the server space because I think we can all agree that your iPad should, maintain its content. But in the server space, my experience is that application developers are actually dying to use persistent. They want to make a persistent write cache. But they can't handle this idea that they think something is stored persistently, and when the machine goes down, they lose access to it, right? So persistence is just kind of half of what they need. What's the other half? The other half is the ability to have it shared with other hosts and have it replicated and things like that. And this is exactly where CXL is bringing us, right? With memory pooling and memory sharing. So it's not that persistence isn't what we want. It's that it's only part of the story, and we're going to start seeing that story be a more complete story as we see CXL evolve.
Yeah, and I think Chris Peterson did a very good job of making that point in his talk. So any of you that are watching now, please refer to Chris. And then also Cholman Park did a good job of describing that as well. He was more on the volatile memory side, but making that case for bringing those pieces together. Okay, we're gonna shift gears now to the last segment I'm gonna call sound bites, and I'm gonna kind of recap first. Things I came into this, the problem we're trying to solve is inefficient data movement. One of the key things that's coming is memory tiering, having these different capabilities, different memory tiers. And boy, we spent a lot of time talking about software for enabling. I think those are my three things, but I'm just going to call out names. Quickly give me in your 5 words or less. So very quickly, give me your sound bite, your walkaway point for our listeners. And let's go with Michael.
For computational storage for real this time. That's the sound bite.
Wow, that was more than 5 words, but we like it. Good job. Let's go to your partner, JK.
Virtualization is the necessary thing for enabling computational storage. That's my take.
Excellent. Chris Peterson.
CXL enables efficient AI memory scaling.
Outstanding. Yang.
For green computing.
Very good. Let's see. Andy Rudolph.
These technologies are complementary. They're additive.
I kind of like that, especially because you got PM and CS with a plus sign in between behind you. Awesome.
Exactly. Yeah.
Stephen Bates.
It's ironic, but mine is CXL plus NVMe plus software equals awesome.
I really like that. That's
And
pretty good.
I tell you, I made that up before other people started talking about math and complementary.
And we started off, I think we've covered everybody except the ever quotable Jim Handy. Did I miss anyone? No, I don't believe so. So ever quotable Jim Handy, we started this session with you. You, sir, get the last word on our soundbite.
I'm just going to say architectures are going to change to take advantage of it.
I want to follow on questions. Will system designers accept that? Because as a memory guy, they always want the same thing, but faster, cheaper, lower power, but they don't like to change their system. Will systems change? It's a requirement.
They always do. It's just slow. That's all.
Got it. Okay. Thank you very much to all our presenters. Thank you for joining this session. Let me quickly share my screen again, and I will wrap up with the comments about please take a moment to rate our session. I don't know what the rating scale is, but if it's a 5, we want 5 stars for sure. Thank you very much for joining us and appreciate your attendance, and hope you view all of the videos that go along with the panel here today from our speakers, as well as tomorrow's panel. Thank you very much. Goodbye.